Yeah,
So
it just,
it's really fun, and it's like so slow. It's like painfully slow. The only reason it's sort of decent is because it does just interface with all the equipment. But
yeah, but just give me a library and tell me how to use it and leave me alone. And there probably is a C++ library for lab that LabVIEW comes with, or something like that you could use. But anyway, today we're going to talk more about how to implement Huffman. So I wanted to begin by just clarifying what that header file looks like on the compressed file, and then because I feel like I was not entirely clear about it on Friday, and then I want to demonstrate my Huffman, and then we will go into almost a member by member description of the Huffman class. So let's go back to homework 5 here. Where is homework 5? It's a typo? Yeah. Okay. Down at the bottom here, what I want you to think about when you're writing out the header, and this is really, you could save a couple of bits by thinking about this in a little bit different way, but it's really not important. When we did this example last time, at the end, the root node of the Huffman tree has index 29. So what you're writing out to the file is the root node. In this case, it would be 29. And then you're simply writing out, that the first interior node is here, the next interior node is here, the next one is here, and you're going to stop here. You know that by virtue of the fact that you know the root node index. So you write out the root node index, and then all you write out is the left and the right child. So the header for this Huffman tree would be 29, and then 14, 3, 226, 13, 27, and 0, 28, and you're done. Because what you're going to be doing is reading those numbers from the file. So you read in 29, and then what you do is you fill in the Huff nodes up to and including index 29. And you know that the first Huff node is going to be 26. Okay, and let's talk about the numbers that we're using in Huffman. So the first Huff node in Huffman is at 257, right? And then the root node, the root of the Huffman tree, is somewhere out past that. So let's say it's 260. So I read 260 from the file, and I know now that what I have to do, what I'm going to be getting next, is left-right children for all the nodes up to and including node 260. And I literally use the same node array that I'm using in the compression step, except most of it I'm not going to use at all. I just grab that same node array, which is a member of the class, and I grab the 260 and then left, right, left, right, left, right, all the way up to 260, and I'm done. I have my tree. So let me show you that in the homework write-up. So I have this file ABC carriage feed or line feed, and then CCA line feed. And the header of this file will be 260, which tells me, remember that the interior nodes start at 257. So that means there's going to be a node at 257, 258, 259, and 260. What do I have to do to build the tree? I need the left and right children of each of those nodes, and that's what follows. So the left children of node 257 is 256, then 98, then 10, then 257, 99, 97, 258, 259, and I'm done. And I'll show you how I can build the tree out of that information here in my notes. So let's go back here And we're reading the header from the file to be decompressed. So we get 260. And then what are the children of 260? Well, we don't know yet. We get, oh, good gravy. Sorry, this is not quite the way I want to build the tree. I don't want to start building the tree yet. What I want to do is, here's 257, 258, 259, and 260. This is the root of the Huffman tree. And then I've got left and right children. So once I read the root, I know that I can expect to fill up the left and right children all the way up to that root. So 257 has left child 256, right child 98. This is L, this is R. Then the next one is 10 and 257. Then the next one is 99 and 97. And then the last one is 258, 259. So as you're reading the header from the compressed file, you're essentially just filling in the node array. And remember that this goes all the way down here, and it has the leaves, and then the interior nodes are up here. And most of this, in this example, most of this is unused space. Because again, we're using the node array for both compression and decompression. But on the decompression step, we literally just need this little slice to reconstruct the Huffman tree. Okay, so now that we have this little slice, we can actually build the Huffman tree. 260, go ahead.
Can we just say that slice is like node, left child, right child, enter character, node, left child, right child?
Say that again.
How are we saving that information?
Okay, so how does that thing look in the file itself? So here's the root node, and that's 10 bits. And then there are 1, 2, 3, 4, 5, 6, 7, 8, 9 bits. Each. And in there is 256, 90, is that a 7 or an 8? I think it's an 8. Yes. 98, 10, 257, 99, 97, 258, and 259. And that is the entire header. And I know how many left and right children I need to read. I just read enough left and right children to fill up the node array to node 260. And then after that, what's after this in the file? The actually compressed file, the character codes. So I read the root node, and that tells me essentially how many left-right children I'm supposed to read. I just read left-right children until I've filled up the node array up to the root node. Now, how does this represent the tree? Well, 260 is up here at the top, and it has a left child of 258 and a right child of 259. And then 259, or it doesn't matter, yeah, well, 259 has 99 and 97. 258 has 10 and 257. And 257 has 256 and 98. So there's the Huffman tree. Now, if you look at the example, what follows is this string of binary digits. So I've read the header now, and I'm faced with these binary digits. And in my picture here, having worked this example this morning, 1 is right and 0 is left. I start at the root node and I go 1, 1, so I go 1, 1, and I'm done. How do I know I'm done? I'm at a leaf. How do I know it's a leaf? Not really. Remember, I didn't. Yes, it's less than or equal to 256, or it's less than 257. So this is a leaf since it's less than 257. So 1, 1 corresponds to A. You're going to have to help me here, keep track. So I get A, 1, 1. So now I'm at 0, 1, and a bunch of 1s. So I go 0, 1, 1, and I'm at 98. So 98's a B. And I know again that I'm at a leaf, so I've got the character. Now, what do I do after I get to a leaf? Print the character, dump it to a file, and then what? Go back to root. So it's really just a process of starting at root, going to leaf, writing the character. Starting at root, going to leaf, writing the character. And the bits are going to tell you when you are at the right place. So what do we just do? 0, 1, 1. So now we're at 1, 1 again. That's down here. That's A. 1, 1. Now we're at 0, 1, 0, 1, 1. B. I have no idea where I am now, but you get the idea. So I literally walk through the compressed data 1 bit at a time, and start at the root. And as I read the bits, if I end up at a leaf, I've got my character, and I go back to the root and keep reading bits. And then just keep reading bits. It just does that over and over and over again. Now, let's go to the last few bits here. 0, 1, 0. I don't know that a priori, but I get down to 0, 1, 0. That's left, right, left, and I'm here. And remember what 256 is? End of file. And when I get there, I exit. I'm done. Flush and exit. Questions about that? All right, let me demo my Huffman program. So if you look at my make file, actually I could have done a better job with this, but if you look at my make file, it's here. I think what I ran into this morning, I'm not going to bother. So I've got hzip and hunzip. Let me show you my hzip.cpp, since there's really nothing, I'm not giving away anything there. Here's my hzip.cpp. It's got some fanciness with the argc and argv going on, which I'll explain in a minute. But if you're compressing, I have this Huffman object called h, and it's going to do h count, h build tree, put the header, and code the file. And that does the complete Huffman building and compression. If I call it as hunzip, then it gets the header and it decodes. So the main program is pretty straightforward. As you can imagine, the devil is in the details. Before I go and talk about the details, I want to talk a little bit about what's going on here. There's a bit of Unix trickery going on here. This same program can be used to zip and unzip, and it takes advantage of the argument array, which you guys have seen in here already. So if I call this program hzip, then when I call ./hzip, it's going to use the 0 argument and put it in the string call. And if call is hzip, then it's going to do the compression stuff. If call is hunzip, then it's going to do the decompress stuff. Now, how can I call the same executable with two different names? That's the Unix trickery. If you look at the directory listing here, you'll see that light blue file. That's called a symbolic link. It was introduced in Windows and I think Windows XP, but it's been in Unix since like 1974. And what this lets me do, this symbolic link is kind of like a pointer. It's not the file, it's simply a reference to the file. But if I call it, so let me show you how my program works. I've got this file here. I'm going to get rid of some junk, so ignore this. So I've got the file here, test.txt, which is precisely the file in the example. If I do hzip test.txt and I give it an output file name, test.hzip, say, it's going to read through test.txt, build the Huffman tree, compress it, and dump the output into test.hzip. I've got some debugging information here that you don't need to include in your file. In fact, I'd prefer if you didn't, but I'm just leaving it in there for demonstration purposes. You see, this is reproducing the example from the homework. The root node is 260. The left and right children are as listed there. If I do a file listing, you see that test.hzip has now been created, and in fact it's 4 bytes larger than the uncompressed file. So this is not a great example in terms of actually compressing. Why the extra 4 bytes? Yeah, the tree encoding cost me more than the compression was saving me. But what I should be able to do if I've got my hzip and hunzip working correctly is I should now be able to decompress test.hzip as follows. And I'll put this in test2.txt because I don't want to overwrite the original example. So now, again, more debugging information. Get header is sort of telling me what it read from the file, from the header. And then if I do a listing, I see that test2 is now being created. And thankfully, it's the same size as test.txt. That's a good thing. But I'm not really fully convinced until I see the contents. And they're identical. On the other hand, if you try to look at the contents of, say, test.hzip, that should be totally legible. Yeah.
Oh, yeah, obviously.
Right, because the terminal is trying to interpret those bytes as characters. Right, there's still just bytes in there. In fact, there are 14 of them in there. And the terminal is trying to interpret the bytes as characters, but most of those characters are just junk. It looks like there's a 0 and a 6 and a 5 in there for some strange reason, but the other stuff is junk.
Can you Vim that hzip?
Yeah, you can Vim it and you'll get the same kind of thing, just junk.
Because it stores them as characters even?
Yeah.
Oh, okay.
And I think there is a binary setting. Let's do a brief...
Yeah.
How is it?
So there's the XXD program, which prints binary. So what you can do is in Vim, you can do XXD, and then if you do test.hzip, that'll give you the hex representation. Yeah.
So that's each byte?
Yeah. If you want the binary, then you can pass it a -b flag, and then it prints out the binary.
Wait, is this each byte or?
That's hex. That's 2 bytes.
2 bytes. Yeah, 2 byte chunks. Okay. Can I get it to show me the bytes? XXD?
To get you to show you. Yeah, that's what I said. The dash B.
Dash B, okay.
So XXD, yeah, dash B.
Okay. Yeah, it's cool. I didn't know about XXD. So now you get to see the bytes, and that should be actually fairly useful for debugging purposes. All right. Now, characters are all well and good, and you know it did the \n just fine. I remember when I was testing this, I figured, well, a real test would be to try to compress the hzip binary itself and decompress it and see if it still works. And the first time I did it, it didn't work. And it was painful to try to debug it. It turned out that I had an off by 1, and my program was not encoding byte 255 correctly, or not at all. I can't remember what it was. But byte 255 wasn't in my text file, right? The text file is just all characters between 0 and 127. And so it wasn't doing 255. It took me a little while to figure out what was going on there. So let's test it on the full binary. What we would like to be able to do is compress the binary and then decompress the binary and see if it still works. Sorry.
Can you show us the sizes too?
Yes. So we'll hzip the hzip function, and we'll write it out to hzip.hzip. What else? So we're calling hzip on itself, and it's going to output a new compressed file called hzip.hzip. Not every byte was present, but damn near every byte was present, right? The highest interior node was 510. What's the highest it could possibly be? 513. So what, there were 3 bytes missing? And that's just dumb luck. This, again, shows you the power of computers. Can you imagine trying to build this Huffman tree by hand, for example?
Give me a year.
Right, once you get the algorithm working for a few things, and it's just cool that you can turn it loose. And you can see the full tree here, right? So 510 has left child 0 and right child 509. 509 has left child 507 and 508, and so on and so forth. So let's compare here hzip to hzip.hzip. Not bad. 25K down to 15K. All right, let me unzip. And I'm going to move it to hzip 2. So there's me just reading the header there. Now hzip 2 and hzip thankfully have the same number of bytes. That's a good thing. But who knows whether those bytes have been faithfully reproduced. So what I'm going to do now is copy hzip. In fact, I'll just move hzip 2 to hzip. Hey, I can always recompile. So now hzip 2 is gone. The original hzip has been overwritten. For technical reasons, I need to do this. And now we will see if hzip actually works, still works. Remember, this is the hzip that was compressed and then decompressed. And let's try hzipping hzip to hzip.hzip. And thankfully, yes, it does work. That's the real litmus test. If you've got your hzip, if you think your hzip is working, see if you can compress the binary hzip and decompress it and have it still work. That's not 100% proof that it's successful, but it's pretty convincing.
So, I lost it.
hours of sleep. The abstract was rough.
It's fine. If you think of it, let me know.
Oh, so when it goes through the binary, is it the same thing as just going through a file?
It really is, yeah.
So it's just like you send in the file and then it goes through and grabs the bytes.
Byte by byte, yeah. And to the file system and so forth, there's no difference between a text file and a binary file. It's all just bytes. And it's really just how those bytes are interpreted by the terminal, by VI, and so forth. Other questions? Okay, so you see that in the case of zipping, I just called the binary hzip, and in the case of unzipping, I called .unzip, hunzip, and hzip is the actual executable. hunzip is a pointer to the executable. The key difference here is that this string right here, hunzip or hzip, gets fed into my program as argv0. And so that's the trickery. If you build this symbolic link, you can call the same binary with different strings, and then you can use those strings inside your program to trigger how it's going to behave. And that way the same program does compression and decompression.
Does our makefile work in different?
So I actually wrote a makefile that would do that for me. You don't have to do that. The key is right here using the link command, ln-sf, hzip, hunzip. This creates a symbolic link, a soft link, and it will overwrite, that's the F, it will overwrite an existing symbolic link of the same name. And the original is the first argument, and the pointer is the second argument. I can't remember if I made this makefile available to you, but I will do that. I'll make it. In fact, I can dump it into the examples directory just so that you can see it. Okay, questions before I go on, start talking about member functions? Let's go here. So as we discussed last week, we are going to have the two classes that we'll be using. The Huff node class, which has all of the information for both compressing and decompressing. And then we have the statically defined array, the Huff node node array, that again we will be using to compress and decompress. On the compression step, the potential exists for every slot in the node array to be used. On the decompression step, most of the node array will be unused. What do I mean by that? Well, none of the leaves will be used, so none of the indices from 0 up to 256 will be used on the decompression step. And even the leaves that even the nodes that I do use from 257 on up to root node, I'm only interested in the left and right children. I don't care about the parent. I don't care about the weight. So on the decompression step, the Huff node array is really overkill. There's a lot more there than we need. But since I'm using the same class to compress and decompress, I don't care. And since it's not that much memory, I just do it that way. But if you were really pressed for resources, then that's a place where you would make some decisions about whether you want to allocate that whole array for the decompression stage. But for the compression stage, you need that whole array and every piece of every node.
So basically, when you like write the header to the file, you can decide to write a separate like array of nodes that didn't have all of the extra.
No, what I mean is when you decide to read the header from the file, you could store it in something much smaller than this.
Oh, okay.
And for example, I had you guys writing, I think I have you guys writing a 10-bit root node. Let's go back here. Where is that anyway? There we go. So I had you guys writing it. Why does that have to be 10 bits?
513.
Yeah. Or it could even be 512. 512 also needs 10 bits, I think. So it could be 512 or 513. I could have gotten away with a 9-bit root node on that last one, but I don't know that for sure. Generally speaking, for a generic binary file, I'm going to be running pretty close to that 512, 513 mark, and it's certainly not worth the risk, and there's no way to predict in advance. Yeah?
Is there a reason to, because we know that our first sort of new node thing is going to be at 257, so we could just do whatever the root node is minus 257?
Absolutely, absolutely. You could save a bit or two. Okay, and that's kind of what I'm getting at. So a lot of this stuff seems a little bit wasteful, but if you can work really hard and you can save a couple of bits. And these are decisions that programmers make all the time. You can work really hard and you can save a couple of K of memory. And it's a slippery slope, and it gets us to the bloated, crappy software that we're at today. But I should tell you that it happens in very tiny increments often. And here's an example right here. I'm not willing to work so hard to save the bit. And then some guy after me is not willing to work so hard to save the next bit. It's just the way it is, man. So I'm not going to save that bit unless somebody forces me to do it. Am I setting a bad example? Yes. Why do the next guys have to be 9 bits? Yeah. And I just think I may have thought of... Yeah, I think I have a bug. Yeah. Yeah, I have a bug. Interesting. This is the third time I've taught this class, and I never noticed that before. There better not be a 512 as one of your children, and there easily could be.
So that's if every single byte is used, then it would create children up through 512.
Yeah. So.
Everyone's 10 bits.
Yeah, that's what I've got to do to fix it. Either that or go with Luke's suggestion of knocking everything down. Now I might want to do that.
Because you can, instead of storing, for example, here 260 as the root node, you could just store 260 minus 256 because
that tells you
that's the last possible, or that's the last sort of leaf, actually. And so then you know that you need to allocate space for 4
right.
of these. Okay.
So just tell me how far past the leaf section I need to be, or I need to go. Yeah. Cool.
Beyond.
No, I might actually make you do it. So you might have to think of something else, because this is an actual bug. Like if I happen to run all the way up and have every byte present, I'm going to break something.
Well, and doesn't it have to be every byte present in the worst possible way, too?
I don't think so. All I need is 512 to appear as a child.
Just do one of
And then I'm done. And yeah, essentially, if the root node runs out to 513, then 512 is going to be the child of something.
It's n minus 1 internal nodes, right?
Yeah. So I think if I have every byte present whether it's a good case or a bad case, it's going to blow up. Sorry? What would it do? I mean, it's going to read. It's going to read. So you wrote out. You would have written out the 512 as a 9-bit, right? And it would have come out all zeros. It would have come out all zeros. And then you would read it in as 9 bits. It would have come in as a 0, and then you would have had the right child of that last node would have been 0, and it should have been 512. That's my bet.
Would you be able to get like a circular tree?
Yeah, because there's going to be 2 0 children. I don't know if it'd be circular just so much as it would be.
You'd have 2 pairs.
Yeah.
Okay.
And you would just be ending up at the wrong. The whole 512 subtree would be lost. So you could potentially lose quite a lot.
I'm surprised that doesn't happen in your average A.out file, you know?
Yeah.
If you don't have everyone in there.
Yeah, that you would have all 255 bytes in, or 256 bytes in there. Yeah. I'm trying to figure out. I'm trying to figure out if maybe there are some if there's like 1 byte that's not represented for some reason that I'm not thinking of right now. Like, I doubt it though. I seriously doubt that there are any bytes that are excluded from a generic binary file by some.
Wait. Wasn't our size 513 though? So our last byte is index 512. So actually the 9 byte.
Ah, yes, thank God. Okay.
We did it, everybody.
There's no bug. Yes, 0 to 512. So the biggest root node could be 512, and 511 is a safe 9-bit number. Thanks, Luke.
You could have gone back and rewritten the entire thing.
I probably would have figured it out as soon as I saw that node array.
Sure, would there be a null in the binary?
A 0 byte, sure.
Okay.
Yep. In fact, let me run that guy again on my debugging. Hey, you're back to above and beyond territory.
No, 256 plus 255.
Yeah.
It's 215. Or is
5.
Sure.
I'm looking for a 0.
Yes. Get a computer.
Oh wait,
So it looks like 0 was in there.
I apologize.
It's fine. When higher back at this point, yeah. Wait, so 0 through 5.
And what's interesting is 0 was the most frequently occurring byte. Is that right?
Is that what R is?
Yeah.
Is frequency?
No, R is the right child.
Right child. Okay, then never mind.
But
Yeah,
since the root node is 510 and the left child is a leaf, that's the most frequently occurring byte. So not only can 0 be in there, it's actually in there quite a lot.
Nice.
Cool.
Oh, well, this would take a long time because we have no real control at it, but it'd be possible to figure out what bytes are missing.
Yeah, I mean, we could figure out which bytes are missing.
Very fun.
Okay, let's talk about this Huffman.
Right.
I feel much better now that there's not a bug that's been sitting here for the 10 years that I've been aware of data structures. All right. Let's look at the header file here. Back to the header file. As I noted before, the EOL character or the EOL symbol is -1, and that's going to represent the end of a list or whether you're going down the tree towards leaves or you're going up following parent pointers. The Huffman constructor for me was taking in the file names, the input file and the output file, excuse me. On the decompression step, it was bringing in, on the compression step, it's bringing in the original file name and the output file name for the compressed information, and vice versa. Count for me, not only did the count, but let me check my notes here. For me, count did a frequency count in exactly the way that I described before on Friday, and then it also sorted the list. And the way that it sorted the list was it called the insert function essentially on every node. Remember how the insert function works? We'll talk about that in a second too. In fact, let's talk about insert right now. It's a private member function. So insert will take a given node and insert it in the tree in ascending order. Sorry, not into the tree, into the list. Remember that we have to have this sorted list because we join two nodes under a new node, and we take those two guys off the list and we insert the new node into the list, and we do that over and over and over again until we run out of nodes, leaves.
Would it be, I don't know, I guess would it behoove us to put it in order, or to just throw it on the end and then sort? Because we're doing like a bubble sort, then it would take a lot of iterations, but it would only really be doing the one.
I don't think you save anything by doing it on the fly. On average, I don't think you save anything by doing it on the fly.
Okay.
And you're not doing a bubble sort here.
Yeah.
So you fill up this static array. You've got all the weights for this static array from 0 to 256, and then you're essentially going to start at the first one and insert it into the list, then the second one and insert it into the list, and the third one. And none of these guys are actually moving. All you're doing is updating their next pointers, or the head pointer if necessary, if it's going on at the front of the list. So, for example, insert. For my insert. The first thing I do is check empty list. And if the list is empty, obviously you're just going to set the root pointer or the head pointer to the first nodes. And you can actually just start that off when you're building the initial list. You can just take the first node and point the head pointer at the first node. Let me think about whether that's always safe. Yeah, I think that's always safe. So check the empty list, and then what you're going to do, if you don't have an empty list, is you're going to traverse the list. And I used a prev and a cursor, and essentially stop when, or insert, I guess. We're going to insert node I before cursor and after prev. In other words, between the two. If cursor equals end of list and you haven't inserted yet, then just append to the list. So there are kind of three main cases. The empty list. Actually, you know what? We can combine the empty list with the front of list. So there are kind of two possibilities in that first bullet point. Either it's an empty list, in which case it's a trivial insertion, or the thing coming in is less than or equal to the first guy on the list, in which case you move the head pointer to the guy coming in and you make the next pointer point to the previous first guy on the list. Does that make sense? If you get past that first step, you want to start moving through the list where you have a prev and a cursor and they're moving in tandem down the list. And when the guy that you're trying to put in is less than or equal to, is greater than or equal to this guy, then you want to shove it in between prev and cursor. And then the last case is your cursor gets all the way to the end of the list and you haven't found that spot, then it belongs at the end of the list. Questions about that? So it's not a very sophisticated sort.
Be greater than or equal to the, don't we need a slightly different condition? Because that would mean, say we had a list that had weights 1, 1, 3, and we wanted to stick 4. Then we would get to cursor, the weight of the cursor would be 3, the weight of what we wanted to insert would be 4.
When the cursor guy is greater than or equal to the guy I'm trying to put in.
Oh, sorry,
I might have said it backwards. But when the cursor guy is bigger than or equal to the guy I'm trying to put in, then I drop it in between. Bigger than or equal as opposed to strictly bigger, because I don't want to do any extra traversal. There's no point. So bigger than or equal. As soon as this guy is bigger than or equal, stick the node in between. And remember, you're not actually moving nodes around. You're just moving pointers around, indices. Okay. Insert is a really important function. You have to write and debug as you go along. These things are notoriously difficult to debug. Harder even than the bitstream function. So keep that in mind. Try to test as much as you can. And a lot of times writing good tests requires work. Writing little test programs that test a particular member function takes some work. For example, this frequency count program, you should run it on a file that you know the frequencies of. Like, for example, the one in the homework, ABC, carriage return, CCA, or whatever it is. Run it on that, and then check the weights, right? The weight on A, the weight on B, the weight on C, the weight on the carriage on node 10. Then once you've got that frequency count working, you're still in the insert function. You run insert, and then you see if when you do the traversal, if you're printing out the nodes in weight order, in ascending weight order. And you really shouldn't move on until you've got that thing working to your satisfaction. We'll talk more about the baby steps and some of the other member functions on Wednesday. Till then.